It's time to continue with the next session. We got a few more talks. The first one was from Syun'ichi Shiraiwa, who is a long-time user and collaborator, and especially mentioned the author and the main developer for MFEM. But today he's going to talk about his work on fusion, magnetic fusion, radio frequency wave simulations in hot plasma. That's part of the, I think it's part of the SciDac project that we're on together. Syun'ichi was at MIT, now is in Princeton Plasma Physics Lab. Syun'ichi, please take it away.
Yeah, hi, thank you. Thank you so much for the introduction. So I changed a little bit of the title to emphasize that this is the radio frequency wave simulation in hot magnetized plasma using differential operator for non-local conductivity response. So, so what I'm going to talk about is as it in. Wait a second. So wait a second. Okay, as the title said, this is a wave simulation. This is about wave simulation of hot plasma. Just to define what plasma is in this context, the plasma is a bunch of charged particles freely moving everywhere, but confined around the magnetic field line. They don't collide each other, so it's called almost collisionless. And so, but also, there's a strong external magnetic field, so therefore each particle draws this kind of gyro motions. So then, if you have the impose a RF radio frequency wave in this plasmas, what would going to happen is every point of around this trajectory of particle feel the electric field. Then that electric field acceleration from the electric field. That information propagate along the magnetic field line, and within this the radius of the gyro motion, indefinitely without instead of. So this is not really typical physics process like diffusions, and so you can imagine that therefore the some electric field information in one places can be connected in other places pretty easily. In fact, therefore we call it the dielectric response of this. In other words, direct response is the response of this plasma to the external field becomes non-local, and therefore the response is often written in a Fourier space or wave number space, like this one in this equation. So J, you can see that the argument is not position X, but wave number. J, the current is a product of conductivity and electric field. As you can see that if you translate this Fourier do the Fourier transformation, you can it go back to the real space equation, which is convolution integral. So the question is, I'm going to figure out is how do we incorporate this kind of non-local physics into the full wave simulation using finite element? So just to introduce a little bit of our work. So we have been using this finite element modeling for the RF waves in the plasmas in a variety of situations. Here I put up a couple of simulations in the people in our group. The leftmost one is electromagnetic ion cyclotron wave in the magnetosphere. So basically this, we have the star here, and the electromagnetic field by the planet is like this shape, and the wave field is excited on here due to the something like solar wind. And the middle one is ECR thruster simulation. As you can see, this was done by the Alvaro Sanchez in our group. He did the earlier work when he was in Spain using MFEM and in 2D simulation, and recently he also expanded in the 3D simulation. we also do our main topics is actually fusion plasmas, and we did built a pretty large RF wave simulation. This in the tokamak plasma. This is the one of simulation showing the the propagation of high harmonic fast wave in NSTX spherical tokamaks. All of them basically, so what they are doing is solving the frequency domain Maxwell equation like this one. And the key point here is this conductivity here is it depends only on position and frequency, but wave number. So in other words, this is local, it's called local approximation. Now there is a work and simulation code which can handle the non-local response especially in the fusion community. And there's various approaches which has been developed, but each of them have actually various limitations. One major successful, one of successful approach is so-called full spectrum method, which basically the approach is basically instead of using finite element basis, which is local or support is limited in space, it uses this spectral ansatz. So, and electric field current is expressed in the superposition, the old Fourier mode. As you can imagine, this is Fourier mode, so it is the simulation domain is little bit limited by square or some simpler geometry, but this has been very successful in our field. As you can imagine, this approach, a full spectrum method, coupled all the result in the fully dense matrix, and it is actually costly. So there's several works to make it simpler and more efficient. One of successful approaches is construct a differential operator using this kind of Taylor expansion of the conductivity tensor. And then if you have K perp, you replace K in a differential operator. Typically, this approach does do only treat up to second order. So therefore, because of nature of the Fourier expansion, you can handle up to, this is valid only when K perp. This wave is small. In other words, the wavelength is reasonably large. And there are a few other approaches which I don't go into detail, but essentially the point here is each of them has its own limitation. Sometimes it requires simpler geometry compared to the 3D simulation I showed in the previous slide, or not generic enough and does not work very well with finite element. So what shall we do with the finite element? And the thought behind this is to look this problem in the context of green function. This is just to remind what was green function. So suppose you have some differential operator L and partial differential equation like this. Then in the Green's method, what we do is put delta function on the right-hand side and solve this equation. And then if you find this G, then for the arbitrarily right-hand side, F, you can write down the solution like this convolution integral. So if you view this method of Green's function in our context, essentially what is happening for us is we already know that G, because G is the Fourier transform, the conductivity in K space. So we know the G, and then we need to find L. Let's say if we can find L, then we can think about solving this kind of coupled partial differential equation. Top one is the usual Maxwell equation, but then it is coupled using electric field on the right-hand side, and then this operator L on the left applying to the J hot, and this current, which is a current induced due to the RF electric field in the plasma, and this J coupled to the Maxwell equation. Well, so how do we find L? That is the next question. It turns out that we can actually use something called rational approximation. And it turns out that it is very simple if we view this problem in the wave number space. So let's say we have J as a product of conductivity times electric field. What I'm saying is we'll expand this sigma in a way like this rational form, then take each of them and write down this way, right? Then we move this denominator to the right-hand side, then use the same same replacement rule to produce this partial differential equations. So the difference between the previous, just going back, this approach of the constructing the differential operator, usually what people has been done is use the Taylor expansion. Instead, what we are proposing is to do the rational expansion, and then move this denominator to the right to the left-hand side. By doing this, there's several benefits of doing this. One, because this is a rational expansion, therefore, this approximation is valid for all range of K-pop. It includes only up to second order, and of course, there's no convolution spectral. In other words, convolution spectral basis function, so there's no global coupling of degree of freedoms. We need to be careful a little bit on this for several things. One is we are talking about solving the coupled partial differential equation made from E and J, not E itself. So we are definitely talking about a larger linear system. Also, this expansion is just an approximation, so it's not really derived from kinetic theory or something like that. So we need to be careful in terms of verification. Okay, so now if some of the audience here might remember this presentation in 2022, it turns out that actually there was a hint there in the last year, which is this work by Tobias Dovalt about the fractional Laplacian. And I'm not going into detail, but essentially what has been done in this work is very similar to the approach I mentioned in the previous one. The difference here is that our conductivity is tensor. So instead of one diffusion coefficient, we have 3 by 3 total 9 parameters, and also those conductivity has a spatial dependence instead of just a uniform simple numbers. So now you might think if I have 3 by 3 metric tensor and there's a lot of terms, then if we do it a rational expansion, maybe degree of freedom might explode significantly. But it turns out that the situation is not that bad. The reason is because our conductivity kernel, especially for the Maxwellian plasmas, which we care for as a first application, all the time is written using Bessel function, weighted by this exponential weight. And therefore, there's an algorithm called modified AAA algorithm, which using that, we can expand many of the Bessel function using the same root. In fact, this compares two cases. One is expanding the 7 Bessel functions using 5 poles, and this one is same things but using 7 poles. And pretty much all the terms, pretty much very good approximation is achieved using only 5 to 7 poles and 7 poles. Okay. I need to touch one more thing. which is perhaps specific to the wave equation. Which is energy conservation or self-adjointness. The coupled equation I mentioned earlier, if you write in a block diagonal form like this, and when this is the then this L1 in the off-diagonal element becomes breaks the self-adjointness when the plasma is non-uniform. In order, if you break the self-adjointness, of course, wave energy is not conserved, which is not not physically reasonable. In order to avoid it, it turns out we need to symmetrize the matrix like this way. So you can see that L appears here and L appears here. And this 3x3 block matrix doesn't seem to be admission as a first glance, but if you eliminate this second and third current component, and if you write down the equation only for the electric field, it becomes actually emission. So let me move on some simulation results. First application test we did is mode conversion of electron Bernstein wave, which is the electromagnetic wave injected from electrostatic wave generated in the plasma. So in this simulation is 1D simulation. Wave is injected from right of this simulation domain, and we assume the plasma density is going up like this. At certain point, wave this bottom figure is wave number spectrum, and you can see that as you propagate, as wave propagate into wavelengths, wave number becomes small, in other wavelengths become large, but then at some point in the middle of the plasma, there's some very short wavelengths more excited. And simulation result is like this, as you can see. So wave is injected from this one. So you can see that wavefront is moving left one. But on the other hand, in this inside, you can see that those very short wavelengths mode corresponding to this high K component appears, and then wavefront is moving rightward. In other words, even the wave is going left toward the left, this is called backward wave, and this electrostatic wave becomes wavefront propagate rightward. I just note that this, if you expand this region, wavelength is like 0.75 meter, which corresponds to what is expected, this dispersion relation on the left. I'll skip this one a little bit. No, I need to go through this. I'm sorry. We further investigated if this really simulation conserve the wave energy. For the waves in the plasma, wave energy is not fully carried by so-called Poynting flux, but also carried by the particle thermal motion, which is called kinetic energy. So we need to compare these two terms. It turns out that you can see that wave, when the equal speed term, this Poynting flux at the beginning of the simulation domain coming from the right of the simulation domain is completely converted to the kinetic energy, which is T, like left. So in fact, as we anticipated, this model can conserve the wave energy, which is good. Now, we further extended this to the 2D simulations. We are still testing this. There's a little bit, I said this is preliminary. The reason is because the operator in 2D or 3D becomes a perpendicular vector Laplacian, which doesn't exist in MFEM right now. So for now, for this testing, we replace this perpendicular vector Laplacian as just a vector Laplacian. And then we change this vector Laplacian this way, the div curve and curl gradient div and curl operation. Both of them can be filled as in the using MFEM bilinear integrators. And simulation result is like this on the left. Wave is injected from this, and the area inside this circle is plasma. And as you can see, that wave is it's similar to the previous one. You can see that the wave become very short wavelengths more excited like this. And if you expand this, wave propagation pattern is similar again. So from outside, wave front is moving leftward. Then in this region, very short wavelengths mode, wave front is moving outward. Okay. Let me summarize. Of course, this is still toy model and need further invest in the verification, but this is quite promising for us. Let me summarize. So we are looking into the construction of differential operator to handle the nonlinear plasma direct response using finite element. And the new approach doesn't use convolution integral or spectrum basis and include only up to second order derivative, which is good for using a finite element to field the matrix. Test simulation mode conversion of electron Bernstein wave is quite promising. Wavelengths agreed well with what is expected in the dispersion relationship. And energy is conserved, and Poynting flux from outside convert 100% to kinetic flux. And also we are working on the 2D simulations. Still, there's a lot. This is the beginning of work. We actually didn't have this idea until this spring, so it's quite new. And there's a lot of questions need to be answered. First is, does this approach scale really to the 3D? And what is the boundary condition if the plasma to touch the wall? We need to answer this question to really generate this approach. And we are still looking at the relatively simple Maxwellian plasmas, and we need to look into the, if the plasma become relativistic. And lastly, as I said before, the approach is based on the is a rational approximation, is not derived from the kinetic theory. It's interesting to ask if such a derivation is possible. Thank you so much.
All right, thank you. Wow. Really interesting talk, Syun'ichi, and I love that it has connection with something that came in the previous workshop. That's awesome. All right, maybe a question or two. Let me ask something real quick. What is exactly Laplacian port?
This one?
Yes.
So this perpendicular is a Laplace, is a vector Laplacian, but only Laplacian, gradient is taken only for the perpendicular to the external magnetic field. So if you have x, y, z, for example, you don't take the gradient in the x direction if the magnetic field is oriented with x direction. We need to take the gradient y and z. And then in the plasma, direction of magnetic field changes everywhere, so it becomes quite complicated.
So is that like a tensor coefficient that's like singular?
Yeah.
So you can think of it as if you have a vector.
Yes, tensor coordinate. Yes.
Like a B transpose or something.
Yes. B transpose as a tensor. You need to we need to subtract that component from the vector Laplacian.
So that has a huge kernel. Everything in any function in just this one variable that you don't take the gradient with respect to is in the null space.
But you don't need to invert those Laplacian part, right? They are added to some other operators. Is that?
Yeah, there is there is a mass matrix contribution from this D.
Okay.
Yeah. So it's not really fully null space.
Okay, but it's near null space, so it depends on the coefficient. It's still be challenging for the solver. Anyway, very interesting.
Thank you so much.
Anyone else? Any quick questions from anyone?
Yeah, maybe a short one. Does this also include colloidal magnetic field or only toroidal?
Yes, this particular one already has a toroidal magnetic field, so it's actually toroidal magnetic is orienting in a counterclockwise. So therefore, the wave launched from here and then once bounce and coming to the little bit, like 20 degree up, then start to propagate inward. That is what is happening here.
Okay, interesting.
All right, thanks, Syun'ichi. This
Thank you so much.
Really interesting. I didn't know about this work. It's super cool.